everyone, welcome back to the lectures in Introduction to Multi-Agent Systems. In the previous lectures, we derived some conditions which would ensure the leader-follower controllability for undirected networks. So how do these properties change when the network now becomes a directed network? This is something that we'll explore in today's lecture. Let's get started. Let us start by defining the objective of this lecture. In today's lecture, as mentioned before, we consider a diagraph, say G with a vertex set V and an edge set E. There are n minus 1 followers and 1 leader in the network. As before, the dynamics of the system is governed by the well-known Laplacian flow, as given below. xf dot xl dot is minus L, the Laplacian, multiplied by this, and then the leader is subject to some external input U. This is exactly the same framework as we discussed in the previous lecture. Again, as before, the Laplacian, as we know, is a square matrix of dimension n cross n. And what we do is, since we have assumed the network to have just one leader, we say that the nth node in the network pertains to that of the follower. Let's mention it. Sorry, the leader. Nth node is the leader in the network. This is the entry pertaining to the leader. What we are left with here, let us call this as LFF. LFF marks the submatrix which tells us how the agents are interacting, how the followers are interacting with each other. And what does this tell us? If you see here, again, this is exactly the same framework as before. So let me simply write x dot equals minus of Lx here. Then we simply multiply xf and xl here. And this, as before, is LFL. From here, we get the following. The follower dynamics can be extracted as given below. xf dot is LFF, negative of it, minus sign here. Also has the input term. Let's complete this part. It must also have an input term. Now it's complete. So then we write the follower dynamics as xf dot equals minus of LFF times xf plus, again, minus of LFL times XL. This is how the followers or the state of the followers evolve with time. What is the input to the system? If you see here, If we look at the larger network consisting of both the leaders and the followers, then we see that there is an external input U, and that external input affects only the leader node in the network. And this leader, in turn, through this equation, affects the followers in the network. So indirectly, the external input affects the followers as well. Now, as before, the question that arises is, can XL, which acts as the input to the subnetwork consisting of only the followers, can XL now control all of the followers in the network, which is what we are primarily interested in. To sum it up, we say that we are interested in determining the conditions under which the system becomes leader follower controllable. Let us see a quick example. Consider the diagram shown in this figure. Here, the node in green, as written here, acts as the leader node of the network, and this leader node receives an external input given by U. The followers in the network are the nodes in blue, which are node 1 and node 2. Let us now write the Laplacian matrix for this system, or we can directly write up the Laplacian flows. Before that, let us remind ourselves of something. We know that XF, the state of the followers, is a 2 cross 1 vector consisting of the states of nodes 1 and 2, and the transpose of this. And XL, since we add the last, or since we index the last node in the network as the leader, XL is nothing but X3. So the reason behind doing this is just to make the computation slightly neater. Now when we apply the Laplacian flow, we get x dot is equal to minus Lx. If you remember, we also have an input term. We'll see very quickly what that input term is equal to. Node number 1 has an out degree of 2, and node number 2 has an out degree of 1. It is connected to node number 3. Node number 3 is a sink node, so the entire third row becomes equal to 0. As before, we split the Laplacian into these parts, where this is our LFL matrix, and this submatrix shown here is LFF. This entire matrix, now we can write multiplied by XF and XL. On the LHS, we can write X dot as being equal to XF dot and XL dot. And this can be directly written as 0 and U. Remember that we can also write it in this manner, but since we know that U affects only the leader node, we can also write it in this manner. So this is a modified form of the Laplacian. So in our case, we have XF dot is equal to minus of 0, 1 times XF minus LFL minus 1 times XL. This is the dynamics of the followers in the network. As discussed before, in this framework, we are interested in checking whether or not the system is leader-follower controllable. In order to do that, we are now interested in checking the controllability of this leader-follower controllability. let's write conditions for leader follower controllability. In order to do that, let's remind ourselves of the dynamics of the followers given by xf dot is equal to minus of LFF times XF minus LFL times XL. If you notice, much like the undirected case, here as well, the dynamics of the followers is very similar to the standard LTI model that we know, state space model, where this is our A matrix and this is our B matrix. We can now easily write up the controllability matrix. Controllability matrix, if you remember, is given by C and is equal to B AB A raised to the power n minus 1 times B. Then in our case, it becomes equal to C equals minus LFL, then LFF times LFL, the minus sign gets cancelled, and this goes up to minus 1 raised to the power n, LFF raised to the power n minus 1 times LFL. From the previous lectures, we know that we can now simplify this controllability matrix simply by writing the spectral decomposition for the matrix LFF. So again, let's proceed the very same way. So the spectral decomposition theorem tells us spectral decomposition for the matrix LFF. It tells that we can write LFF as being equal to Vj, V inverse, where V, as before, is nothing but an n cross n matrix with the eigenvectors of LFF as its columns. And the matrix J is a Jordan matrix. In the case of an undirected graph, what happens is LFF turns out to be a symmetric matrix. And the spectral decomposition theorem says that if we have a symmetric matrix, then when decomposed, it will always have a Jordan form which is diagonal in nature. Because of this nice properties, we could arrive at some conditions which directly led to the leader-follower controllability of the system. However, in the case of directed networks, LFF is not necessarily a symmetric matrix. Let us write this important thing. In the case of digraphs, LFF is not necessarily a symmetric matrix. Hence, J may or may not be a diagonal matrix. Now, we have finally arrived at some conditions which seem different from the undirected counterpart. Before we proceed, like we did for the undirected case, let us substitute this value of LFF into our controllability matrix. It would give us C is equal to minus LFL. Now, instead of LFF, I'll write Vj V inverse times, and this will keep going. The last entry here is minus 1 raised to the power n. Again, Vj V inverse raised to the power n minus 1 times LFL. Please note an important point just earlier mentioning the dimension of LFF. The dimension here is n minus 1 cross n minus 1, meaning when we now try to write up its controllability matrix, it will have the same dimension. Hence, when we are writing the controllability matrix here, extend it only up to, so this is LFF raised to the power n minus 2. Do the same modification here. This is equal to n minus 2. Okay. Now we are ready to apply some tools, or we are ready to do some manipulations to this. So let's do that. We can write now LFF can be multiplied with the identity matrix, and now V times V inverse is equal to identity. So now we can write this way, LFL, and we saw before that Vj V inverse raised to the power something simply becomes equal to Vj raised to the power that same number times V inverse. We showed it in the previous lecture, so I'm not going to do it here again. But this becomes equal to j raised to the power n minus 2 times V inverse times 12. So as you can see, V appears on the left of every term here. Hence, we can simply pull it out and write the C matrix in this form. But let me highlight it in a different color because again, later we are going to use it. I pull out V now, and then I write the rest of the things as they are. V inverse LFL times J into V inverse LFL. This goes up to minus 1 raised to the power. Again, this should be n minus 1, n minus 1. Please make note of these changes. N minus 1, K raised to the power n minus 2, V inverse LFL. What can we now say about the Jordan matrix J in the case of a directed graph? We can say the following things. Now we know that J depends on the matrix LFF and its eigenvalues. The eigenvalues now can take the following forms. The eigenvalue of the matrix LFF, let's say the eigenvalue be lambda, it can either be simple, in which case we say that the algebraic multiplicity is same as the geometric multiplicity and is equal to 1. Lambda could now be repeated, but still be something that's known as semi-simple. In the case of a semi-simple eigenvalue, we have AM again being equal to GM, but now they are greater than 1. And the third case is when it is simply a repeated eigenvalue and is not semi-simple. In this case, the algebraic multiplicity is not the same as the geometric multiplicity. The nature or the structure of the matrix J depends on how exactly eigenvalues of the matrix LFF. What we'll now do is we'll analyze the exact structure of J for each of these cases. Let's start with the first case where we say all the eigenvalues of LFF are simple. In this case, J is a diagonal matrix. And we know already how to analyze the conditions for leader-follower controllability when J is a diagonal matrix. In short, we can simply write all the conditions for leader-follower controllability of undirected graphs hold here as well. The reason being that when J is a diagonal matrix, ultimately the controllability matrix boils down to the exact same form that we get for the undirected case. Now, let's look at the case when all the eigenvalues are semi-simple, or let's say simple, either of the two. So in the second case, we consider that all the eigenvalues of LFF are now either simple or semi-simple. In this case as well, J turns out to be a diagonal matrix, hence all the conditions for leader-follower controllability of undirected graphs hold here as well. The interesting behavior occurs or arises when we have an eigenvalue which is now a repeated eigenvalue but is not semi-simple. So that takes us to the third and the most interesting case. We say that all the eigenvalues are repeated such that the algebraic multiplicity of the eigenvalues are not equal to their geometric multiplicities. In such a case, J, the Jordan matrix, becomes a block diagonal matrix such that J can be written as, suppose J1 is the first block, J2 is the second, and say the last one is some Jk. The dimension of this matrix is n minus 1 cross n minus 1. And what does each Ji look like? The ith block takes the form J is equal to, this is the ith block. Now, when we specify the ith block, it is incomplete to say only Ji. Let us modify this a bit more. We say Ji, the ith Jordan block, suppose it is the function of some eigenvalue lambda and has a dimension, let's write it lambda I, say. Or let's call it some lambda, just lambda. And the size of the Jordan block is Mi, meaning this is a square matrix of size Mi cross Mi. Then all the entries along the diagonal are simply equal to lambda, and the off-diagonal entries, the super diagonal entries are equal to 1. And the rest of the entries in the matrix are directly equal to 0. Please notice this important property. Along the diagonal, we have the eigenvalue, and along the off diagonal, we have the entry 1. This is what every Jordan block in this bigger Jordan matrix looks like. Every every block here takes the following form. With this, we are now getting closer to analyzing what exactly, when we substitute this Jordan block in the controllability matrix, what form will it take? But before we can actually write it, let us try to understand one more thing, which will help us with our analysis. Whenever we have a block diagonal matrix, and suppose we raise it to some power p, in that case, j raised to the power p is simply each Jordan block raised to the power p. This is what j raised to the power p will look like. So let us analyze what will j I, the ith Jordan block raised to the power p, exactly look like. We can calculate it a bit more precisely because we already know exactly what is the structure of the matrix. So let us do that. We are interested in calculating the powers of the ith Jordan block. This is equal to ji raised to the power some p without loss of any generality. Let's write it as lambda I. However, please note that it is possible for one eigenvalue to have multiple Jordan blocks, meaning it is possible for J1 and J2 can be associated the same eigenvalue, in which case we'll get lambda 1 equals lambda 2. Now, coming back to our Jordan block raised to the power p. This now becomes equal to lambda I raised to the power p, p1. Lambda I raised to the power p minus 1. This, the last entry here is equal to p raised to the power some ji minus 1 j multiplied with lambda I p minus ji plus. Second row becomes equal to 0. Again, lambda I raised to the power p and so on. I'm not showing all of the entries here, but just the important ones. Let's write up the last but one row. This entry is 0, this is 0. This entry here is equal to lambda I raised to the power p, and the last entry is equal to p times lambda I raised to the power p minus 1. Similarly, the last column has just one entry non-negative given by lambda I raised to the power p. This is what the power of the ith Jordan block looks like. Now, with this information, what we'll do is we'll now go back to the controllability matrix and substitute this value of ji there and see what we get. So now we'll analyze the controllability matrix. If you remember, the controllability matrix takes the following form. This is some V inverse LFL. It'll have a minus sign here. And the next term is equal to J times V inverse LFL This goes up to minus 1 raised to the power n minus 1, j raised to the power n minus 2, V inverse times LFL. Let's do something. Let us replace the term V inverse LFL by some column vector R tilde. Instead of writing R, we are writing instead R tilde just to distinguish that we are now looking at the directed case. If you open up the original paper in which they introduce the notion of controllability, there the undirected case had this represented using the notation R. Just to be consistent, we have written R tilde here. Now, let us compute what each of these entries will look like. In order to do that, let's look at the pth column. Let's write the pth column of C takes the following form. It is equal to minus 1. Instead of the pth column, let's take the p plus 1th column. The reason being that then we can write it as j raised to the power p. So this is equal to minus 1 raised to the power p plus 1 j raised to the power p times R tilde. Let's see what this looks like. Let's keep this as it is. What is j raised to the power p? J raised to the power p is simply each of its Jordan blocks raised to the power p. And what does any Jordan block raised to the power p mean? It means this form. So let's do something. Let us copy this entire matrix and write it here. Since we're going to write a big matrix, I've reduced its font slightly. And let me get this here. Remember that this is just one of the Jordan blocks. And we have k such Jordan blocks, meaning let's make the matrix even bigger. This matrix, as you see here, is multiplied by R tilde. R tilde is an n minus 1 cross 1 vector. So let's multiply this. So before that, let me mention that we know that these are all zeros. And instead of I, let's make the Jordan block slightly better. So this is the first Jordan block, so we replace lambda 1. Lambda I with lambda 1. This is 1, and this is 1, and this is 1. In the second Jordan block, we replace these with lambda 2s. And this goes on. And the kth Jordan block has lambda I as being equal to lambda k. Some k. This gets multiplied with the vector R tilde. So let us write it very carefully now. Just to remind you, the dimension of the first Jordan block is say M1 cross M1. Now let us write up the first M1 entries of R tilde. It will be equal to R1 tilde going up to RM1 tilde. Then the second Jordan block has, say, a size of M2 cross M2. Then the corresponding entries of R tilde vector are written as R tilde M1 plus 1 with up to R tilde M1 plus M2. Similarly, the dimension of the last Jordan block is, say, some Mk cross Mk. Then the corresponding entries of R tilde are given as R tilde N1, N1 minus 1 minus Mk minus 1 again, and the last entry being R tilde N minus 1. Now, let us simply do the multiplication. Obviously, the entry starting from R tilde M plus 1 to R tilde N minus 1, they do not affect the first Jordan block at all, meaning the first Jordan block gets multiplied only with these entries. Similarly, the second Jordan block gets multiplied with these entries of R tilde. Correspondingly, the last Jordan block gets multiplied with these entries. So what do we get as the output? Simplifying this entire expression leads us to this column vector. Size of this is equal to n minus 1 cross 1. Do is we take this particular entry and substitute it in the controllability matrix here in the place of j. Then there'll be j square in the next one, going up to j raised to the power n minus 2. Now, we want the system to be of full rank. In which cases can this matrix C lose rank? It loses rank if either its columns become linearly dependent with each other, or some of its rows become linearly dependent with each other, or perhaps one of the rows or columns becomes identically equal to 0. Under what scenario can that occur? So let us start by trying to figure out under what scenarios can one of the rows of this column vector here, one of the entries of this column vector here becomes equal to 0. For that, let's try something out. Suppose we claim that R tilde M1 is equal to 0. It doesn't matter what lambda 1 is. We just say that the only condition is, say, R tilde M1 becomes equal to 0. In that case, if you observe, the M1th entry of this particular column vector becomes now equal to 0, because this is equal to 0. And the last row here, when it will get multiplied with this, if this entry is 0, then this multiplication will turn out to be 0. What happens in that case? Suppose, say, let us make this observation. If R tilde M1 or R tilde M1 plus M2 or R tilde N minus 1 minus Mk. If any of these entries is equal to 0, then one of the entries, or rather, we can be a bit more precise and write, then the M1th or M1 plus m2th or n minus 1 plus mkth entry of minus 1 raised to the power p plus 1 j raised to the power p times r tilde is 0. What happens in that case? This would imply that when we now write the controllability matrix, all of its entries corresponding to that particular row this is m1th. This is if the m1 plus m2th. So this should actually go up to, instead of writing n minus 1 plus kmth, we can simply write if the n minus 1th this is the last entry, which is n minus 1th. Then whichever entry, if the, so we say, if rm1 equals 0, then the m1th row of C is identically equal to 0. We can be a bit more precise and say that if the, we say that if our m1 or our m2 or our, the last entry, sorry, r tilde, n minus 1, 0, then C has at least one row with all 0 entries. Which implies that C loses rank. Hence, we have now found the condition under which the system does not remain leader-follower controllable. And note that this result does not say anything about the eigenvalues of LFF. Rather, it simply talks about the product. It simply talks about R tilde. And what is R tilde? R tilde is the product of V inverse and LFL. Let me show you here. This is R tilde. Sorry. V inverse times LFL. Hence, the condition for controllability is that when we do this multiplication, none of its entries corresponding to, if this is the ith Jordan block, the corresponding entry of R in R tilde must not be equal to 0. This should not be equal to 0. Similarly, the last entry given by this should not be equal to 0. If this happens, then the system definitely loses rank. So now we have found a condition which can ensure that the system remains leader-follower controllable. Let us see a quick example to understand this. Let us look at the diagraph shown here. This is the same diagraph that we saw before, hence I've already written up what exactly the follower dynamics will look like. Now let us try to figure out what is the Jordan decomposition of LFF. LFF is given by VJV inverse, and our condition for controllability requires us to check what happens to V inverse LFL. For that, of course, we need to first calculate what are the eigenvalues and what are the corresponding eigenvectors. Already done the calculation, but please pause the video here and try it out by yourself. What do you get the eigenvalues to be? In this case, the eigenvalues turn out to be, let me first write up the Jordan block, the Jordan matrix. In this case, the Jordan matrix turns out to be a diagonal matrix. And V, which consists of the eigenvectors of LFF, is given by 1, 0 and 1, 1. And the inverse is given by 1, 0, minus 1 and 1. Then, in order to check the controllability, we evaluate R tilde. R tilde, if you remember, is equal to V inverse times LFL. V inverse is equal to 1 minus 1, 0, 1. We multiply it with LFL is minus 1 and minus 1. First entry is 0, the second one is equal to minus 1. So what does the condition for controllability says? It says that whatever is the size of the Jordan block, let's say if it is of size 1, then the corresponding first entry in R tilde is what we have to check. The second Jordan block is of size 1, hence overall this appears or this corresponds to the second entry here. So these are directly the entries that we need to look at. And what observe, you see that the entry corresponding to the first Jordan block is actually equal to 0, which according to our condition implies that the system is not leader-follower controllable. So this implies it is not leader-follower controllable. Let us now look at yet another example. Let us consider the diagraph shown in this figure. Note that this diagraph is very similar to the previous example, the diagraph in the previous example, with the only difference is in the diagraph shown here, we have an edge from 1 to 3, and that edge has been deleted here. Now this is how we can calculate the dynamics of the follower. We use the Laplacian flow, we apply input to the third node, which again acts as a leader in this case as well, and then this is what we get as the dynamics of the follower. Now, the eigenvalues of LFF now are actually repeated, equal to 1 and 1. And the Jordan block, this is the eigenvalue, and the Jordan block J is actually of this form. So now if we apply V inverse F, so I'll directly write what the value of V inverse. But before that, let us observe something here. This is the Jordan matrix of LFF. Meaning now, what is the size of the Jordan matrix? You see that this entire thing is the Jordan matrix. Hence, its size is equal to 2. So we need to now check what is the last row and which row is this. This is the second row. So when we evaluate V inverse R, we need to look at the second entry of that vector. Meaning, if we compute R tilde given by V inverse LFL, we get this to be equal to 0 and 1. what we see here is one of the entries is again equal to 0. However, now it doesn't affect us. Why? Because we only need to check the second entry. And we see that the second entry is actually non-zero, which implies the system is now actually leader-follower controllable. With this, we end the topic of controllability of interconnected systems. In the next lecture, we'll look at dynamical systems and some of its properties. Thank you.